So, welcome to this last lecture on game theory. In this lecture, we'll be seeing how to solve game by simplex method. For solving the game by simplex method, we will first have to formulate that game as LPP. Because of the connection between the game theory and simplex method, both get benefited. Like some of the knowledge in game theory will be useful in simplifying the simplex method, and some of the things in simplex method will help in solving the game. All right. So we will first have to formulate this as the LPP. Okay. So what is that we have to find in this game? We have to find the proportion of course of action A1, A2, A3 for player A, and let that proportion be x1, x2, and x3. All right. And we also have to find out the proportion of course of action B1, B2, B3 for player B, and let these proportions be Y1, Y2, and Y3. Right? So here I write let um, xi be the proportion of course of action AI, and yi be the of course of action course of action bj. All right. Yj, I'll be calling that as yj as the proportion of course of action bj. All right. We will prefer to formulate this problem right in the beginning. Anyone would choose to formulate this game through our own point of view, that is through the point of view of player A. Okay, so we'll be formulating this game through the point of view of player A. And what does player A wants? Player A wants to maximize the game value. Objective for player A is to maximize game value. So I write here formulation with respect to player A. All right. So objective for him will be maximize z equal to game value. I don't know what is the game value. I simply write it V here. Actually, this is to be written in terms of the variable, decision variable x1, x2, x3, etc. But I don't know how to write it in terms of the decision variables right now. So I just keep that, just defer writing it in terms of x1, x2, x3. Right now, I write maximize z equal to v. Now, what will be the constraint? Okay, subject to. Okay. Now the expected payoff, expected gain to player A if player B plays B1 will be 3 into x1 plus 1 into x2 minus 2 into x3, because these are the proportion, and these are the payoffs if player B plays B1. So the gain to player A is going to be 3x1 plus x2 minus 2x3. Okay, this is also going to be the loss to player B. Expected loss to player B if player B plays B1. Right? Now, I, for writing this as a constant, this has to be related with something either less than or greater than equal to. Now that this I know is the expected loss to player B. Okay, loss to player B uh, if he plays b1. All right. Now this loss to player b will be definitely greater than or equal to v, because v is the game value for us. V is the game value for us, and this has to be greater than equal to v. Why this has to be greater than equal to v will be interesting to see. Okay, see here. The objective function is written through the point of view of player A because A wants to maximize his gain. But the constraints are written through the point of view of other player who wants to minimize his loss. All the constraints will be written through the point of view of will be written by having the knowledge about player B. It is, you will always see that the constraints are from environment and the objective function is of your own. All right. So here the constraints will be written through the perspective of player B. So this is the loss to player B if he plays B1. Okay, and this v is the game value. It is maximum for player. It is the maximum value for player A and minimum value for player B, because B wants to minimize the game value, minimize the losses. All right. So through the perspective of player B, this will be minimum value. This is minimum value. We are writing the constraint through the point of view of player B, through the perspective of player B. Okay, this is V through the perspective of player B is minimum. Okay, and for V to be minimum, this value will be equal to or greater than this V. Okay, it is for that reason there is a greater than equal to sign, and once you are convinced with this, writing another constant, for example for b, etc., will be for example for b. So we'll be writing the constant for b on the same lines. What it will be now, the last two player b, if he plays b2, will be minus 4x1 minus 3x2 plus 4x3. Okay, so here I write minus 4x1 minus 3x2 plus 4x3. Again, this has to be greater than equal to V, which happens to be the minimum value for player B. Because this constant, this side is the loss to player B. If he plays B1, this loss will be definitely greater than or equal to V. It cannot be less than V, because if we want to keep V minimum, this value has to be greater than that or equal to that, not less than. Okay, so this is the constraint if player B plays B2, and likewise the third constraint will be 2x1 minus 7x2 plus 7x3 greater than equal to V. Okay, and lastly x1, x2, x3 will all be greater than equal to 0. This is the formulation of the game through the point of view of player A. Okay, only the objective and the variables are associated with player A, and the constraints are more because of player B. Okay, because of our understanding of player B. Okay. Similar way, we can have the formulation through the point of view of player B. In that case, the objective will be minimize z equal to v. In that case, the objective will be minimize z equal to v, right? So that we will be doing little later. But there are some unusual things in this formulation. Okay, let us first take care of those unusual things in this formulation. All right. There is one more constraint which we forgot to write. Right. What is that constraint? You know that sum of x1 plus x2 plus x3, x1 plus x2 plus x3 is equal to 1. This sum is equal to 1. You know that? Because these are proportion and they must sum to 1. So what we will be doing now, there are some unusual things in this formulation. One unusual thing is your objective function is not having the variables of the problem. It is simply maximize z equal to v. Okay, and it is not containing x1 x2 x3. This is one unusual thing. And another unusual thing is right hand side must be a constant. It should not be a variable. Here it is variable. So we will be taking care of one each unusualness, and we will be converting it to usual type of formulation. So first of all, for having the constant this side, we'll have to divide both the sides by v. So this constant will become like this, right? First constant will become 3x1 by v. Now what I do, x1 by v I'll be considering as x1 dash, x2 by v I'll be considering as x2 dash. So here I make a general convention, xi by v is equal to xi dash. Okay, so my constraint will now become what? 3x1 dash plus x2 dash minus 2x3 dash, where x3 dash means x3 by v will be greater than equal to 1. Alright, v by v is 1. And second constraint likewise will be minus 4x1 dash minus 3x2 dash plus 4x3 dash is greater than equal to 1. And the third constraint will be 2x1 dash minus 7x2 dash plus 7x3 dash greater than equal to 1. Alright, greater than equal to 1. And now if I try same thing in the fourth constraint, that is x1 plus x2 plus x3 is equal to 1, I am seeing that my left hand side will be usual, like x1 dash plus x2 dash plus x3 dash is equal to 1 by v. Okay, the problem for which I was doing all this is coming once again in front of me, but still I don't worry about it. I continue doing that. X1 dash plus x2 dash plus x3 dash is equal to 1 by v, because I am dividing both the sides by v. Okay, so some of the unusualness in this group of constraint I have sorted out, but some unusualness is still remaining. Okay, what is that remaining? Or something which was usual has converted to something unusual. Okay, and I lastly write my objective function as maximize z equal to v, which I can write as minimize z dash equal to 1 by v. Maximizing v is minimizing 1 by v. Okay, now I have two unusual problems in this formulation. One is I don't have the regular variables of the problem in my objective function. Now the variables in my problem are x1 dash, x2 dash, x3 dash. But in my objective function doesn't contain those variables. And another problem is there should be a constant on the right hand side, but in the fourth constant I don't have constant, that is 1 by v. Okay, all right. And so now what to do? what I'll be doing, I'll be coupling these two problems together, and I will be getting the solution of both the things in one shot. Okay, right? I know that here there should be regular variables like x1 dash, x2 dash, x3 dash, and I know here there should not be 1 by v, there should be some constant, right? So what I do, I know 1 by v is equal to x1 dash plus x2 dash plus x3 dash, that I put here in place of 1 by v, and I don't need this constraint as such. Okay, this constraint has been utilized to regularize my objective function. So my formulation now becomes maximize z equal to what, x1 dash plus x2 dash plus x3 dash. All right, subject to 3x1 dash plus x2 dash minus 2x3 dash greater than equal to 1, minus 4x1 dash minus 3x2 dash plus 4x3 dash greater than equal to 1 again, and 2x1 dash minus 7x2 dash plus 7x3 dash greater than equal to 1 again. This formulation is very easy to write from this problem. Just look at this. X1 dash plus x2 dash plus x3 dash is my objective function in place of x1, x2, x3, subject to 3x1 dash plus x2 dash plus x3 minus 2x3 dash greater than equal to 1. Likewise, just by seeing this, minus 4x1 dash minus 3x2 dash plus 4x3 dash greater than equal to 1. All right hand side will be 1 only. All right. But now the question is, can I write x1 dash, x2 dash and x3 dash greater than equal to 0? Okay, can I write? As far as the proportions are concerned, I know them to be positive, but what about game value? Because x1 dash is x1 by v, x1 is positive definitely, but is v positive always? No, v is not positive. You cannot be sure about value of v. It may be positive, it may be negative. All right, so you cannot write x1 dash, x2 dash, x3 dash greater than equal to 0. It may or may not be 0, may not be greater than 0. Okay, or greater than or equal to 0. I am not very sure about it. Okay, just for this problem, just check what is going to be the game value. Okay, so here before I solve the problem, I myself is not obeying the practice. Okay, but you do. So minimum guaranteed gain is minus 4 here, and minus 7 here, and minus 2 here. All right, and maximum possible loss is 3, 4 and 7. So minimum amongst maximum possible loss is 3, and maximum amongst minimum guaranteed gain is minus 2. So your game value is going to lie between minus 2 to 3. That means it can be negative also. Okay, so if it can be negative, how can you claim about x1 dash, x2 dash, x3 dash, which is xi by v? You cannot be sure that this will be greater than equal to 0, and if it is not, you are not sure about it, you cannot use simplex method, right? So there is a trick now. You will have to make sure that this is greater than equal to 0, and we will do that. Let's see how. Okay, if I know that my game value is going to be positive, then only I can claim that all the variables of this form x1 dash, x2 dash, x3 dash will be greater than equal to 0. But if game value lies between -2 to 3, then I cannot. So I will have to reformat my game so that it is sure to me that game value will be definitely positive. Okay, there is one property of this game, that you can add constant quantity to this game, to all the values in this game. Okay, and if you do that, the proportions for the new game obtained won't be different than the proportions, optimal proportions which you obtained for this. Game value may be different, but the proportions for both the games will be same. What we will be doing, we will be adding some constant to this matrix, whereby we are sure that game value will surely be positive. We are going to modify this game. Okay, for time being we'll be modifying this game. Okay, so let's do that. So it can be very easily proved that if you add certain constant to all the elements in the P of matrix, all the values in the P of matrix, the proportions which you will be getting will be same as that you get for original game. Only the difference will be in the game value. Game value will increase by the amount, by the element, by the value which you add in all the elements in the original game. So for the purpose of getting the linear programming problem, LPP formulation, which can be easily handled by simplex method, we will be adding certain constant to the mm, given game, because here we are knowing that game value, there is a risk of getting game value negative. Okay, and once the game value is negative, we will not be in position to solve this formulation by simplex method. So what is the best value which I can add to this game? Okay, so what I find, even if I add 2, this will turn to 0, but I don't want that maximum to be 0. Okay, so what I'll be doing, I'll be adding little more value. You can add any constant. Only the thing which you have to make sure that the maximum should turn positive. Zero doesn't have its own sign, so adding two will put us in little trouble sometimes. So what we'll be doing, we'll be add 3 to this matrix. All the elements in this matrix will be added 3. So let's see what happens now if I add 3. Okay, I'll be getting new matrix, right? So this matrix, the new payoff matrix, will be having new elements, right? The courses of action A1, A2, A3 for player B, B1, B2, B3, little modified game for the sake of solving it by simplex method. If already your maximum is not negative, then you don't have to do all this. This is to be done if your maximum turns out to be negative. Okay, you have to add something to it. So I have decided to add 3 to the game. Okay, so from that game I will be adding 3 to this game. Okay, so this 3 plus 3 will become 6, then minus 4 plus 3 will make it minus 1, 3 plus 2 will make it 5, 1 plus 3 4, minus 3 plus 3 0, minus 7 plus 3 minus 4, then minus 2 plus 3 will make it 1, 4 plus 3 will make it 7, and 7 plus 3 will make it 10. To all the elements I have added 3. Now as you see here, the minimax and maximin both are expected to increase by 3. Just look here. Minimum guaranteed gain, once again I will be pointing here, minimum value is minus 1, here it is 0, and here it is 1. Okay, and maximum possible loss, this actually you don't have to do because it is simply a common sense that you have added 3, so 3 will get added to all this mgg and mpl, so that's what you are seeing. Here, I'm sorry, this is minus 4, not 0, this is minus 4. Okay, then maximum possible loss, here it will be 6, here it will be 7, and here it will be 10. You see that all these mpls are 3 more than mpls here, maximum possible losses here. So minimum amongst maximum possible loss is 6, and maximum amongst minimum guaranteed gain is 1. Now your game value will be between 1 and 6, that means it will be surely positive. So now I will be formulating this game through the point of view of player A, and then I will also be formulating this game through the point of view of player B as well. Okay, so formulation. Now I will be doing the things directly. Formulation of game with respect to player A. All right. So I can directly do that because I knew the pattern of formulation. So what is that? Now it is, if I want to do the formulation through the point of view of player A, initially it looks as maximizing the game value, but the transformation process which you have seen had converted this maximize type objective function to minimize. Here there is a mistake. It is basically minimize. Okay, it's not maximize, it is minimize. This was minimize because I turned this to minimize, and that retains here. So initially it start with maximization, and while we do our processing, it turns to minimize, and finally it remains minimized. So our formulation will be initially having the objective function maximize type, but later it will turn to minimize. Okay, so it is minimize z equal to, now I can write x1 dash plus x2 dash plus x3 dash. Right? What are x1 dash, x2 dash, x3 dash? We have already seen those, and those are x1 by v, x2 by v, and x3 by v, where v is the game value and x1, x2, x3 are the proportions. Right? Subject to 6x1 dash plus 4x2 dash plus x3 dash will be greater than equal to 1, and then likewise minus 1 x1 dash, okay, plus 0 x2 dash plus 7 x3 dash will be greater than equal to 1, and last constraint will be x1 dash plus 7 x2 dash plus 10 x3 dash greater than equal to 1. Okay, and now if you question, can I write x1 dash, x2 dash, and x3 dash greater than equal to 0? Yes, you can, because x1 dash is x by v, x1 by v. X1 I know that it will be definitely positive because it is a proportion. V, I have made sure that it will lie between 1 and 6, that means it will also be positive. So all these variables will have positive value. So this problem can be solved by simplex method. Okay, but what you are seeing, the objective function is minimized and the constraint are greater than equal to type. So you are a bit reluctant to solve the minimization problem as far as LPP is concerned, and particularly when the constraints are greater than equal to, right? So it will be better if you have maximized type objective function, and you know very well that maximized type objective function will be there for player B, because player B that way is a dual of player A, right? We have seen so far in game theory that A has the objective of maximizing the gain and B has the objective of minimizing the loss. So player A and B are dual of each other. Now we have seen that objective function for player A starts with maximization of V and turns to minimization of x1 dash plus x2 dash plus x3 dash. Now if I write the formulation, now everything is going on patterns that you once you have understood this. So keeping this understanding at the back of your mind, I'll be directly formulating the game now for player B. Okay, formulation of game with respect to, that is for player B. Okay, the for player B, right? So obviously for player B, it is minimization of game value. So objective function initially will be minimize z dash equal to V. And your constraints will be initially like 6y1 minus y2 plus 5y3 less than equal to 1. Now I will be doing the complete formality of the formulation. So for B, it will be minimize z dash, I'll be writing is equal to game value. Okay, subject to constraint. Now this objective function is for B, but the constraint will come because of player A. Okay, because of the conditions imposed, conditions visible due to player A. So subject to. Okay, now expected gain to player A will be, if he plays A1, it will be 6y1 minus y2 plus 5y3. Okay, this is the gain to player A, gain to A if A plays A1. Now, how much that this gain can be? What will be the upper limit of this gain? Now, this is player A will always be trying to maximize his gain, but the maximum limit of gain to player A, we know that is V. That is V, that is the game value. Okay, so if that is to be maximum, if V has to be maximum, this will have to be lesser than that. Okay, the expected gain to player A if he plays A1 will always be less than equal to V, because this is maximum for player A, maximum um, um, for player A. Right? So once this is understood, you can write another constraint directly: 4y1 plus 0y2 plus minus 4y3 less than equal to V again. This is if player A plays A2, alright? And the third constraint will be y1 plus 7y2 plus 10y3 less than equal to V again. This is if player A plays A3. Alright? And one more constraint will obviously be there: y1 plus y2 plus y3 is equal to 1. Now, as we did last time, we'll be dividing both the sides by v, and therefore here there will be one, here one, and this y1 dash, y2 dash, this y1 and y2 and y3 will turn to y1 dash, y2 dash, y3 dash as x1, x2, x3 turn to x1 dash, x2 dash, x3 dash, where y1 dash here means y1 by v. All right, but this also is going to be y1 dash plus y2 dash plus y3 dash is equal to 1 by v. So what we do, we change our objective function from minimize to maximize. Maximize z, maximize objective function will be equal to 1 by v, and this 1 by v value will be putting there. Therefore our formulation will become maximize z equal to y1 dash plus y2 dash plus y3 dash, okay, subject to 4y1 dash plus 6y1 dash, this is first constant, 6y1 dash minus y2 dash plus 5y3 dash less than equal to 1. Then 4y1 dash plus 0y2 dash minus 4y3 dash less than equal to 1 again. Then y1 dash plus 7y2 dash plus 10y3 dash less than equal to 1. Alright. So it is very simple to write this formulation directly based upon this. Only the thing which is to be remembered is for player B. Finally, the objective function will turn to maximize with the constant types less than equal to, and for player A, the finally the objective function will turn to minimize with the constant greater than equal to. Now you have the choice which problem where you can solve this by simplex or this by simplex. You have to solve only one problem by simplex method. All right, you have to solve only one problem by simplex method. All right, you should prefer to solve this problem by simplex method, right? The reason is objective function is maximized and the constraints are less than equal to, and you have seen in simplex method which I have taught to you, that the maximization problem happens to be more comfortable to solve. The problem with less than equal to type constraints happens to be more comfortable to solve as compared to the problem with greater than equal to type constraint, by particularly by simplex method. So now that this formulation is over with last constraint as y1 dash comma y2 dash and y3 dash all greater than equal to 0, right? Now we'll be solving, or you can solve this by simplex method. I'll not be presenting complete simplex solution of this. I will simply be referring to the optimal iteration for this problem. Okay, if you solve this by simplex method, the optimal iteration will look like this. All right, here is the optimal iteration for this problem. Okay, directly. Hmm. For this formulation, I have the optimal iteration, right? So this is the optimal iteration only. Optimal table, right? So in optimal table, you have all the variables y1 dash, y2 dash, y3 dash, s1 dash, s2 dash, and s3 dash. Coefficients of y1, y2, y1 dash, y2 dash, and y3 dash in objective function, as you see, is 1. And right hand side constant initially is 1. That is a peculiarity of the LPP formulation of the game. Okay, all objective function coefficients of the variables involved in the formulation of game will finally be equal to 1, and the right hand side of the constraint is also 1. So after solving that problem by simplex method, this is the simplex table finally, right? Wherein you are getting y1 dash equal to 8 by 43, s2 dash is equal to 11 by 43, and y2 dash is equal to 5 by 43. And finally, it means that y3 dash is equal to 0 because that is not here in this table, right? But I wanted y1, y2, y3. How to get that? Okay, I have all cj minus vj value and also the value of z. I know z equal to 1 by v. Okay, because in this problem minimize z was v, so and finally my objective function is maximize z. So that will be 1 by v. So z is 1 by v here. Okay, z is 1 by v, and as z is 1 by v, I have got game value for the game which I have solved. V will be equal to 43 by 13. Here I write that. Therefore, v is equal to 43 by 13 because z is 1 by v and z is 13 by 43. So v will be 43 by 13. Now what about y1, y2 and y3? y1 dash is 8 by 43. So y1 dash I know equal to y1 by v. Therefore y1 is equal to y1 dash into v. Okay, y1 dash is 8 by 43 and v is 43 by 13. So 43 cancels and I get y1 equal to 8 by 13. y2, if I want to get y2 will be equal to y2 dash into v. So here it is y2 dash is 5 by 43 and v is 43 by 13. So y2 I get 5 by 13. Okay. And y3, because y3 dash is 0, y3 will also be equal to 0. So I got the proportions of courses of action for player B. Now, need I solve? Do I need to solve the another simplex method for getting the proportions of courses of action for player A? No, I don't need to because those are available to you here. If you recall that Cj minus Ej value for slack variables, Cj minus Ej value for slack variables is the value of corresponding dual variable. And if you look at this problem and this problem, they are dual of each other. Okay, I can write ahead of this constraint. For example, x1 dash, x2 dash, and x3 dash. Okay, I will be getting this problem. If I write x1 dash, x2 dash and x3 dash ahead of each of the constraint and form the dual with this variable, with this dual variables, I'll be getting this problem, that is the problem of A. Okay, that is I'll be getting the problem of A. So these two problems are dual of each other, and if I get the Cj minus Ej value uh, the for the slack variables of post constraint, that will be the value of x1 dash. S1 dash, s2 dash for second constraint, that will be the value of x2 dash. Okay, so here I have the values of Cj minus Ej values of s1 dash, s2 dash and s3 dash. These are the values of x1 dash. Okay, this is the value of x2 dash and this is the value of x3 dash except for sign. Sign you change from negative to positive. So here I know x1 dash is 6 by 43 and x1 is x1 dash into v. Alright, x1 dash into v, x1 dash I have got 6 by 43, v I know 43 by 13. So finally it comes 6 by 13. X2 dash is 0. Okay, that means x2 is also 0. Okay, x3 dash is 7 by 43. So x3 will be 7 by 43 multiplied by 43 by 13. So I get is 7 by 13. Okay. Now just check whether you are right or not. The sum of the proportion should come equal to 1, and that seems to be coming 1 here, because if I add all the proportions I get it 13 by 13 here also and 13 by 13 here also. My game is solved. So strategy for player A is what, 6 by 13, x2 is 0 and x3 is 7 by 13. Strategy for player A, and strategy for player B is what, 8 by 13. Y1's value is 8 by 13, y2's value is 5 by 13, and y3 doesn't appear here, so its value is 0. All in all, you must be cautious that sum of all the ingredients of the strategy should be equal to 1. Okay, here it is 1, here it is 1. Okay, and game value, even though we have found out it as 43 by 13, 43 by 13, but uh, it is for this game. It is for this game, and this was not our original game. Our original game is this one. Okay, our original game is this one, right? This is our original game. Okay, to this game we have added 3. And now, as our purpose of adding 3 has been served very well, we have got the proportion, we have got the game value, but for this. So for getting the game value, proportion for which we have obtained for this will be valid for this game also, not just valid, they will be the proportion for this game also. Okay, so adding any constant to this game doesn't change the strategies will remain same, game value will be different. Now that I have added 3, now is the time to subtract 3 from the game value. So my game value for this problem after adding 3 is 43 by 13. So from that 43 by 13 I will be subtracting what I added. I added 3, so now I'll be subtracting 3. So 43 by 13 minus 39 by 13 gets me 4 by 13. Alright, 4 by 13, so that is the game value. Okay, alright. So this is how to solve the game by simplex method. Now, why we have learned this when we had another simple methods? This connection is bringing us a facility. Now suppose say you have certain problem, general problem, general LPP. So what you may do with that LPP, for example, I will be taking certain LPP here, that maximize Z equal to 3x1 plus 4x2 plus 2x3, subject to x1 plus x2 plus x3 less than equal to 9, 2x1 plus 3x2 less than equal to 15, and 4x1 plus 3x2 plus x3 less than equal to 24, and x1 x2 x3 greater than equal to 0. Now what you can do with this, you can substitute this 3x1 as say y1. First of all, you will be dividing, you will be converting all these values to 1 by dividing whole this equation by 9, whole this equation by 15, and whole this equation by 24. Then after doing that, you will be making a substitution that 3x1 is equal to say w1, 4x2 is equal to w2, and 2x3 is equal to w3, and you will be converting this problem in terms of w's, right? Mm, what will happen because of that, as we are seeing that the formulation of the game is having one peculiarity, that all the coefficients of the objective function are 1 and the right hand side constant is 1. Okay, what will happen because of that, if we do that kind of transformation in this lpp to make it look like all the right hand side constant equal to 1 and the coefficients of all the variables here turn to 1, then what we have here on this side will be nothing but a game. Okay, and now that we have turned LPP to a game, like we have turned game to LPP formulation, we can turn LPP to a game. And once the LPP is turned to game, all the methods which are available in game theory become available to LPP. Okay, we can reduce the game by dominance principle. We can eliminate some of the constraint here, making the thing simple. We can use augment method. We can use some more methods, which and this transformation may lead to generation of some more things. Okay, so here with this note, we will be stopping in game theory. So, thanks a lot. Thanks a lot. Mm, okay, we'll stop here.